Hello folks, welcome back to another award-winning video. We are working in section 11.3 this week, the Law of Cosines. First thing I want to mention here is that this is something we talked about in the last lesson, but every triangle has 6 direct measurements, 3 angles and 3 side lengths. To solve a triangle, when I ask you to solve a triangle, it means you have to find all the missing side lengths and angle measures. In order to do that, you must know at least 3 of the 6, and that's a minimum requirement. Now for each figure below, the check marks indicate a known measurement and the question marks indicate an unknown. And what I'd like to do here is just go next to each triangle and write the congruence postulate or theorem that matches the known information. So for this picture right here, I know 2 angles and the side between them. That's clearly angle side angle. And if we have angle side angle information, that guarantees congruence. For this picture right here, we have 2 angles known and a side not between them, so that's angle side, and that does guarantee congruence. Then down here we have, let's see, we know an angle and then we know 2 sides, but the angle is not between the sides, so this is a side angle. And remember, side angle does not guarantee congruence. It's leads to something known as the ambiguous case, where you can get multiple solutions for the same given information. So these are applications for the law of sines, and what I want you to look for anytime you see anytime you have a picture of a triangle is you should label the knowns and the unknowns. And to use the law of sines, you need to look for anytime you know an angle and then the side across from it. Angle, side across from it. Or in this picture, for angle side angle, we know a side, but we don't know the angle across from it. Unless we use the triangle angle sum theorem, we could find this third angle, and then we would have the angle side opposite pair known. So anytime you know an angle and the side opposite, you're thinking law of sines. And that's something that you should be looking for when sketching out these problems. For applications involving law of cosines, a little different situation here. So for this example, we know 2 sides and the angle between them. That's clearly side angle side info, guarantees congruence. And in this picture down here, we know all 3 side lengths, but none of the angles. That also guarantees congruence. So what we're going to do here today is we're going to talk about the law of cosines and then the type of examples where you'll see applications of law of cosines. So anytime you have side angle side info or side info, you should be looking to apply the law of cosines. So here it is. Okay, given a triangle with angle side opposite pairs of alpha and A, beta and B, gamma and C, the following equations hold. So right here, this is the law of cosines. A squared equals B squared plus B squared plus C squared. Come on, fast. A squared equals B squared plus C squared minus 2B times the cosine of alpha. And what I want you to recognize there, if I were to cross out the right-hand side of this equation, if I just got rid of all this stuff right here, hopefully you'd see that that looks a lot like the Pythagorean Theorem. In fact, it is a lot like the Pythagorean Theorem. It's the general case. It can be used for any triangle, not just right triangles. If alpha was a 90-degree angle, then this whole thing here would be 0, and it would look just like the Pythagorean Theorem. Okay, so the other way you'll see that here is that, we have cosine of alpha equals basically this equation rearranged so that cosine of alpha is on one side of the equation. And what you'll see me do with that is I'll say alpha equals the cosine inverse of this expression right here. What I'm going to do now for you is I'm going to draw out the other forms of this equation, because I know some students may only need to see this form here on the left and then just adjust your thinking so that you can use these 2 examples for any triangle. But some students, if you label it ABC in a certain way, it might be helpful for you to see these other forms. There you have it, folks. There's the other versions of the law of cosines. Again, they're all the same. They just have the parts oriented in different ways. So if we use this version right here of a squared equals b squared plus c squared minus 2bc cosine alpha, just show you what that means here. Let's say we have this triangle up here, and I'll call this side A. And that means this is angle alpha. And this would be side B and side C. The length of a squared is going to be equal to the length of b squared plus c squared minus 2 times b times c times the cosine of the angle between them. So that's law of cosines. Let's go ahead and use it in example 1. First thing I'm going to do is sketch a triangle that's approximately the right size. I'm just trying to, what I try to do here is make that angle down in the lower left-hand corner about equal to 50 degrees. So let's go ahead and label my parts. This will be 50 degrees, and that's point B. A has a side length across from it of 7, and C has a side length across it of 2. So that's the information that I'm given. What I don't know but have to find is alpha, gamma, and lowercase b. So the problem here lays out the strategy we should use. It says solve by first finding b. So I know two sides, the angle between them. I can find the side opposite them by using the law of cosines. So to find b, I can say that b equals b squared equals a squared plus c squared minus 2ac times the cosine of beta. Well, what I'm going to do here is I'm just going to write this. I'm going to take the square root of both sides and erase this b squared. So I can do that. I can take the square root of both sides. Remember, you don't have to worry about the positive and negative square roots because this is a side length, so it is going to be the positive square root. All right, so let's plug in what I know. We have a value of a that is 7, and c is 2. Minus 2 times 7 times 2 times the cosine of 50 degrees. Got to take the square root of that whole thing. And when I do that, I get an answer of b is approximately equal to 5.916. 5.916 units, approximate answer. Okay, what I want to do now is I'm going to solve for angle alpha. And for alpha, I'm also going to use the law of cosines. So this right here, that was law of cosines. And what I'd like to do now is use law of cosines again, but slightly different. I want to use it to find the angle alpha. And if you look right up here, it says cosine alpha equals b squared plus c squared minus a squared divided by 2bc. So I can say that alpha equals the cosine inverse of b squared plus c squared minus a squared divided by 2bc. And let's go ahead and plug into that. Cosine inverse of b squared, which will be that 5.916 value, squared, plus c squared, which is 2 squared minus a squared divided by 2 times 5.916 times 2. Okay, so when you plug that into your calculator, again, in my calculator, I stay in radian mode all the time. So this is going to give me alpha in radians multiplied by 180 over pi, and you'll get alpha is approximately equal to 115 degrees. Okay, folks, we're cooking with gas here. Last thing we got to do now is find gamma. So we've already found two of the angles in this triangle. Let's go ahead and use the triangle angle sum theorem on this one. So just stepping back to review, this was also the law of cosines. Just a different application of it. We found a missing angle rather than a missing side length. And now the last thing I'm going to do is find gamma. It's going to be equal to 180 minus the sum of 50 degrees and 115 degrees. And this is the triangle angle sum theorem. And that gives me gamma equals 15 degrees. And for reference, I'll write that. Triangle angle sum. Okay, so at that point we're done with the problem. We were given three initial pieces of information and we found the three missing pieces. So our solution is side length B, angle alpha, and angle gamma. But I do have a question for you. And here's the question. And the question is, what if we had used the law of sines to find angle alpha? Now, we used law of cosines to find alpha, but let's take a look to see what happens if we had used law of sines. So for law of sines, we would have had the sine of alpha over 7, that's the side across from alpha, equals the sine of 50 degrees divided by the side length across from 50, and that was side length B, which we found to be 5.916. So we can do a little bit of algebraic manipulation here, and we can get alpha equals the inverse sine of 7 times sine of 50 degrees, all divided by 5.916. And when you go ahead and plug that into your calculator, make sure you convert alpha to degrees. You're going to get alpha is about 65 degrees. What's the deal with that? I thought alpha was 115 degrees. Why did we get a different answer using law of sines, which is something that has to be true? So we have another question here, and it's, why is this wrong? So why is this thing wrong? And the answer is simply called the ambiguous case. And the ambiguous case occurs when we use side-side angle information to solve a triangle. And the ambiguous case occurs if we use side-side angle information to solve a triangle, and it's because we can have two angles with the same sine ratio. So 65 and 115, they both have the same sine ratio, but the arcsine function will always give us an output of 65 degrees, not the 115. So you might be saying to yourself, well, Mr. Vass, we didn't have side-side angle information. We had side angle side. And if you go back to the original picture, you can look at that and say, yep, we had side angle side information, and side angle side guarantees. It guarantees one solution. Well, yeah, it does guarantee one solution, but it depends on how you find it. Okay, it guarantees one solution if you eliminate that ambiguous case. So in this case, alpha was an obtuse angle, and the law of sines will only give us angles which are acute. Okay, so that's a warning to you, and I have a suggestion for how you can avoid problems with that in the future. And here's my advice. So that's my advice, folks. Always use law of cosines if you can. You should use law of sines cautiously. If you do use law of sines, go back and check the sine ratios divided by the side opposite. So go back and check to see that sine alpha over A equals sine beta over B equals sine gamma over C. And you can actually just plug those into your calculator, and as a matter of fact, for this triangle, let's go back and see what that sine ratio would have been. I'm going to do the sine of 50 on my calculator divided by 5.916. So hold on a second while I do that on my calculator. Sine of 50 degrees divided by 5.916. So that ratio is about 0.129. You should get that ratio on your calculator every time you divide for this triangle. You should get that ratio for each of these other two ratios as well. Okay, folks, that's it for page 1. We're going to shut this one down and then crank up part 2 here in a little bit.